Familiar with Memorial. We're located on the far east side of Canada on the island of Newfoundland. Um, we represent the province's only university and one of the biggest universities in Atlantic Canada. Our main campus is located in the city of St. John's, which is the home of the chemistry department. And it's actually a pretty exciting time for us at Memorial because we just moved into a few months ago this state-of-the-art $100 million research facility, which I'm actually in my new office now. So it's exciting that we have moved over here. Um, so what type of research do we do in my group at MUN? We are interested in three main areas of research: reaction development, total synthesis of bioactive natural products, and strategic designed synthesis to medicinal agents. But today I'm going to focus on some method developments, where one of our research goals is to develop and utilize new CH activation functionalization methods to access annulated ring-containing systems. And one of the ways that we have been able to achieve this goal is through utilizing the diazo compound. For those of you who are maybe a little less familiar with this class of organic molecule, it's a neutral dinitrogen containing molecule, which has been shown to be very versatile reagent in organic synthesis. One of the reasons for this is owed to the fact that it undergoes relatively easy loss of dinitrogen to generate a carbene intermediate. And carbenes can be different forms. For the purpose of this talk, we'll think of the carbene as a singlet carbene, where we have a lone pair of electrons perpendicular to an empty p orbital, and therefore we can envision the carbene as an amphiphilic type characteristic in reactivity. It can both donate electrons and accept electrons to form multiple bonds. Now, another reason that people have been drawn towards this functional group class is that we can attenuate the reactivity of the developed carbene intermediate by a couple different methods. One is by changing the electronics around the carbenoid center, so we can have acceptor groups, donor groups, or acceptor-acceptor groups, and this will be the main focus of today's talk from my research. But another way that we can attenuate the reactivity of these carbenes is through the activation method. And one prominent method is to decompose the alpha diazocarbonyl in the presence of a transition metal to access a metal bound carbenoid species. Now, these types of metal carbenoids are very useful. They can undergo a variety of selective and reproducible organic transformations, one of which that's fairly important to today's lecture is insertion reactions. In particular, you can have a metal-bound carbenoid, which can undergo an addition reaction with a heteroatom nucleophile to generate a zwitterionic species, which upon 1,2 proton transfer would lead to a net inserted product, where we form two new sigma bonds to the carbenoid carbon, one to the heteroatom and the other to a proton. Now, this is a fairly well-established area of research, but one of the limitations, or something that we could think about expanding on, would be if there was a nice method to form two new sigma bonds to non-hydrogen atom species. So could we create a quaternary type carbon? Could we form two new carbon-carbon bonds? Well, in essence, we can see this in the area of heteroaromatic additions. For example, if you had that same heteroatom add to your metal carbenoid, and then you trap the corresponding zwitterionic intermediate with some sort of electrophile to generate a new sigma bond via delayed proton transfer type approach. And this has been well-established research for heteroatom nucleophiles. And one of the big players in this area is the Wenwao Hao group in China, who was a previous postdoc in Michael Doyle's research group and is well familiar with diazo reactivity, has developed several nice methodologies to show intermolecular and intramolecular reactions of diazo compounds with a heteroatom nucleophile and an appendant electrophile. So the intramolecular reactions are the higher yielding, and they also lead access to a variety of useful heteroaromatic compounds. Now, while this is well established for a net heteroatom H bond insertion, the comparable CH insertion chemistry, which is also well known and documented for diazo compounds, the insertion followed by an annulation event is much less explored. And one of the main contributions to why is due to controlling site selectivity. What CH bond will undergo an insertion reaction with the reactive metal carbanoid that you generate from the diazo compound? It is not controlled by the nucleophilic lone pair of electrons on your heteroatom. So controlling the selectivity is a little bit problematic. Now, when we entered this field of research, there were a few people starting to explore it, and they had relied on methods of controlling slight selectivity through directing group strategies. And what we wanted to come into this was a different approach. We knew that there are a variety of things that we needed to be successful, but one thing that was on the forefront of our mind was to avoid directing group strategies by using a nucleophilic carbon component to control the site selectivity in a CH functionalization. We also knew that the targets that we were making, the products that we were making, needed to be of a desirable molecule class. And related to this, we needed to utilize starting materials that we could rapidly access and evaluate a variety of different electrophile handles that would be compatible with a CH insertion followed by an annulation event. And then ultimately, we wanted to do this utilizing cheap copper catalysis or cheap catalysis systems. Copper is going to be the lead to coming later. So to start off, we thought about a nucleophilic scaffold being that of indole, and we thought of this for a couple of reasons. One, its known reactivity to undergo site-selective CH functionalizations with metal carbanoid species. For example, indole can undergo net C3 insertion when their R group of indole is unsubstituted or is just a proton. Also, you can control the selectivity for a C2 insertion event when R is not equal to a proton via ring opening of this cyclopropane intermediate. So it's well known that indole undergoes reactions site selectively with diazo compounds and the metal generated carbanoids thereof. In addition to this, indoles are very abundant in nature and pharmaceutically relevant target molecules. But more importantly, there's a whole class of organic molecules that contain the indole framework and another fused ring through the nitrogen and the C2 position. And this was what was interesting to us because it would allow us to start by appending an electrophile to a readily available starting material. Indole abundant starting materials through simple alkylation chemistry. We could put electrophiles on the nitrogen and then develop an annulation approach to access a series of bicyclic indole frameworks. So the last thing we had to look for was what type of electrophile we wanted to utilize. We initially started off by exploring an alkyne as the electrophile, and the literature precedent came from Hatayama's group in 2014, who showed that you could do an OH insertion followed by an annulation onto the alkyne via a coniine type cyclization. So with this idea in hand, we quickly accessed the propargyl methyl scatol, and we tried to develop a CH insertion coniine annulation strategy to access these pyrroloindole scaffolds. We started off by exploring copper catalysis, one because it's ultimately was our main goal to use cheap metal source, and copper is well known to participate in both the CH insertion reactions within indole as well as the annulation chemistry. Unfortunately, we saw only a small yield of the insertion product and no desired cyclization from the reaction. We feel that there's some competitive reactivity with this electron-rich electrophile, and I'll get into that maybe a little bit later. But switching to rhodium, we started to see slight increases in yield and started to actually see by NMR the desired cyclization product. Switching to more soluble solvents for the classic rhodium catalyzed conditions, we start to see a little bit more product. However, we could never really force the reaction any further than this 12%. So we started to add additives to promote the cyclization after the insertion had occurred. Using scandium triflate didn't really influence the cyclization. Switching to copper as a co-catalyst did give us a pretty good yield of the cyclization, only at 28%, but for the first time we actually saw a good isolatable amount of material. Silver, interestingly, consumed most of the insertion product, leading to the cyclized product, but also gave some of this six-member ring containing product and about a 20% yield. And finally, the use of zinc gave us what at the time was our best yield of 47%. Now, one of the things I'll mark here is that our limiting reagent, our diazo reagent, is completely consumed in all of these reactions, but our yields are not very high. So we thought maybe this had something to do with the substrate, and if we just move past the methyl group at the C3 position, we might be able to see some higher yields. Unfortunately, just changing the alkyl chain length gave us a great decrease in the yield of the reaction, and putting a phenyl group at that 3 position gave us almost no product. So I asked my grad students, well, where's the mass balance? What are the potential byproducts? Why can't we explain where the rest of the mass is? One of our first initial thoughts was potentially a competitive dimerization of the diazo compound. And I thought, okay, this would be an easy thing that we could experimentally change. We could use a syringe pump to slowly add our diazo reagent so that there's always an excess of the indole around to react with the reactive carbene that's generated. Unfortunately, using syringe pump even for very long addition times over 24 hours gave us no change in the isolated yield. We thought maybe there was some competitive intermolecular reactions with the C3 position of the indole, or potentially cyclopropionation of our electrophilic alkyne handle. And this was predicated by the fact that every time we ran a reaction, we could see a bulk of our mass that looked like both components were there, the diazo reagent and the indole, but there was just too many products to fully elucidate. So what we decided next was if we could change slightly the diazo structure, we might be able to elucidate some of these byproducts. And as a happy coincidence, when we changed to these trifluorodiester diazos, we got an increase in yield to 57% from 47%. And as an added benefit, this unknown mixture that we were unable to identify with the ethyl esters, we were now able to separate by purification and identify as competitive benzenoid insertion products. So this is where our mass was going, and was really the big hiccup in the project. We recognized that we were getting competitive insertion on the benzene ring, and we thought, well, if we put a blocking group at that position, we might increase the yields for the site selectivity at the C2 position of the indole. And this was, of course, after a little bit of optimization, turned out to be a key factor for us. Optimizing solvents, catalyst loadings, and temperatures, we're able to move on to an efficient substrate scope, and I'll highlight here, without the blocking group, we were able to get the yield up to about 64%, but by putting a substituent like an O-methoxy group here, we get a higher increase in yield, presumably by decreasing any of the benzenoid insertion products. We then screened through the diazo groups, and these worked well for acceptor class, so where we have 2 electron withdrawing groups. A little less so when we're using the keto esters, but we couldn't extend this to just the acceptor class of diazos or the donor acceptor class. It was kind of limited to the acceptor acceptors. The reaction conditions were tolerant of a variety of substitution on the benzenoid ring, whether at the 5 or 6 position, a variety of different methoxys or halogens, all giving fairly good yields regardless of the position or location of the blocking group. Alkyl groups, alpha, beta, and saturated systems also worked well as other aromatic systems. Where our methodology starts to decrease is when we start using electron withdrawing groups, whether that's on the benzenoid position or remotely somewhere else, as we'll see in a second. We decrease the nucleophilicity of the indole, and we start to see dramatically lower yields. We can see this when we have a nitro group on the benzenoid ring, but also when there's a cyano group, although I would like to mention that under these reaction conditions, we also get a competitive oxazole formation, which is actually a known literature reaction, and we were able to optimize this a little bit further to functionalize both the 2 position, giving the annulated product as well as forming the oxazole at above 50% yield, although I don't have that shown on the slide here. Finally, and a second to last component of our substrate scope, we looked at the C3 substituents. Everything works well without extending the alkyl group chains. Again, having a blocking group, there is a dramatic increase in yields when we have that blocking group on versus when we do not have that blocking group on the benzenoid ring. And as I mentioned before, when we change the electronics of the indole ring, now we have this alpha, beta, unsaturated system directly connected into the indole nitrogen of the ring. We get lower yields, and this is even seen when we use electron withdrawing aromatics. Finally, we extended the scope by looking at the different ring sizes that could be formed, and up to date, we can form the 6-membered rings, relatively comparable yields to the 5-membered rings, and we can even access a 7-membered ring. And this was research that we published back in 2020. But we knew that there were some limitations with this research project. One, it was limited to terminal alkynes. It could not be internal or alkenes as acceptors. We needed a C3 blocking group. If we don't have that, we only get site selectivity for the C3 insertion. It was very dependent on the type of diazo, and we required a rhodium zinc catalyst system, which the rhodium became a little bit expensive. So in order to combat some of these problems, we thought, maybe we could switch the electrophile source to something that's deficient, which maybe allow us to use some copper type catalysis. And again, some work by the Wen-Hao-Hu group showed that you could do a OH insertion followed by a Michael addition reaction. So we could use an alpha beta unsaturated system. And without going into too much detail, we developed very recently this copper catalyzed a variant of our reaction that undergoes CH insertion followed by a Michael type addition, was able to expand this to a variety of different useful substrates. And we published this a little earlier last year. It's a pretty neat paper with some high selectivities. We form 1 geometric isomer when we do have the triple bond incorporated into our starting materials. I just want to move past this a little bit and talk about another quick area of research in the last few minutes here. It's when we were exploring the initial insertion, we saw these low yields. We thought there might be competitive insertion at another position. This was before we knew it was benzenoid. So I had another one of my grad students try and optimize a reaction sequence where we did an intramolecular insertion followed by an annulation. And this required access to a unique set of starting materials, but there was a known literature procedure by Doyle to access these diazo-indole compounds, which could undergo insertion under rhodium conditions. So I had my student test this out using these diazo-enones, which have a remote beta position to the enone that you can activate without destroying that diazo. And promoting a Michael addition, we're able to get a little bit of this product, but we also recognize that under the scandium conditions, it's cyclized onto the C2 position. However, we weren't really sure what product was formed, because as you could imagine, we could form a carbon-carbon bond between the carbanoid carbon and a C2 position, but we found out that Taylor and Unsworth in 2016 showed a very similar diazo-indole compound undergo a Wolff rearrangement, which gives you a little bit of a structural difference in the connectivity. And because these compounds existed by NMR as a mixture of enol and keto tautomers, it was hard to determine which one we had. So I asked my grad student to make the one that's in the literature and then append the bromide and see, or append the propargyl group and see which one we have. And when Seema, who was the grad student, went back to do this, doing the Michael addition under scandium conditions led to the Michael addition product as the major product, but she also noticed two carbazole products forming under these reaction conditions. We were able to prove the major compound by converting the Michael addition product and then oxidizing, and we could check that out by NMR, but we were unsure about this minor product. In particular, comparing the two NMRs, if the minor product came from a Wolff rearrangement, we wouldn't expect the spectra to be so different between the two carbazole compounds. In particular, the C5 position, which is markedly different, about 1 ppm de-shielded in the minor compound. So after a little bit of analysis, Seema was able to, well, not analysis, a little bit of manipulation. She built a more robust material that we could grow a crystal of the minor product. And it showed us that the connectivity actually was via a different type of rearrangement. So at this stage, we tasked Seema, or I tasked Seema with developing this new skeletal rearrangement type process of these indole diazo compounds. What we initially started off with was the minor isomer, which we wanted to convert that rearranged product into the major isomer of the reaction. And in 2021, we were able to develop some nice copper conditions that help control the reaction here. So I just wanted to kind of end with this little bit of work. Mechanistically, it's proposed to rearrange through this 1-2 shift where the indole can activate at the carbon number 3 position with the diazo carbon, and we can generate a whole series of useful rearranged carbazole scaffolds. With that, hopefully I've shown you that we can develop some interesting chemistry utilizing heteroaromatics and indoles through CH bond insertion and annulation type chemistry. This added project that I threw in here because I thought I'd have some extra time. I realize I'm running a little bit over now. Sorry about that. Is hopefully something that you guys could check out on your own. And coming soon, we're exploring this chemistry in total synthesis, in particular of furan-based natural products. I just want to thank everyone for your attention, my groups, and the funding agencies that have allowed me to do some research. Thanks for letting me go a little bit long. Sorry about that.